This is AP Physics, chapters 3 and 4. Today I want to take a little bit of time to introduce the idea of vectors. So here we have an overview of everything that's in chapters 3 and 4, which is basically the background, the idea of vectors, and then the application of those with regular vectors, and then specifically with projectile motion and uniform circular motion. So vectors are something we talked about last year. The thing to remember about vectors versus scalars is that vectors have two things. Vectors have both a magnitude and also a direction. Scalars, on the other hand, only have a magnitude. So for example, 20 kilometers east, the 20 kilometers is the magnitude, east is the direction. If I had a scalar, for example, time, 15 seconds, the number, the units, no direction needed. Everything we did with vectors last year will apply, but the key difference this year is the use of unit vectors. Our unit vectors are I, J, and K. And the basic idea of a unit vector is it is a vector that has a magnitude of 1 that points in a given direction. And typically those given directions are your X, your Y, and your Z direction. So then the I unit vector points in the X direction, your J unit vector points in the Y direction, and your K unit vector points in the Z direction. So they are not impacting the quantity, they're just tags so that you can easily identify what direction the vector is in. The little symbol above, the caret, is a symbol for a unit vector. A typical regular vector like position or displacement, we would put an arrow over the top of the quantity to represent that it's a vector. But if you have a caret, that represents it's a unit vector. In your textbook, they will bold things that are unit vectors. Now, let's take a look at an example and kind of relate what we did last year to how we're going to express it this year. So a simple case. Car is traveling 350 kilometers at 35 degrees north of west. Well, if we drew this out, we would draw our coordinate system, our frame of reference. 35 degrees north of west, I would come here to west. I would rotate toward the north 35 degrees, and then we would draw our vector, 350 kilometers. We want to find the components of that, and so we're looking for making that the hypotenuse of a right triangle, where this would be the X and this would be the Y. That just involves trig. It is a right triangle, so then we would use trig to be able to find those two sides. Cosine of 35 degrees, that's going to give us the adjacent side X over the hypotenuse 350. Sine 35 degrees, opposite side, Y over 350. So when we solve this down, we're going to get an X value of 286.7 kilometers and a Y value of 200.75 kilometers. That's pretty much how we worked them out last year. Now, B, when we're writing this as a unit vector, well, we're going to use an R for the vector, and then I need to express these as the two components. I know the 286.7 is in the X direction, so I'll write that, and I'll tag it with an I, which just represents the X direction. The 200.75 kilometers is in the Y direction, so I'll tag that with a J. Now, we also have to note that the X direction goes west or left, so that's going to be a negative value. So using unit vectors is just a streamlined way to be able to write out, and in the next one we're going to show how you can use it also to streamline the work that you do. Next example. Airplane is flying 500 miles east, 200 miles 30 degrees north of east, 300 miles 40 degrees east of south. If we initially represent the vectors, 3 different displacements, 500 miles east, 200 miles at 30 degrees north of east, and then 300 miles 40 degrees east of south. Now east of south, we have to go to south, and then from south rotate 30 degrees east from there. So those are our three vectors. We know we're going to have to find components of each and combine those components. But I'm going to streamline what we're doing using unit vectors. So R, our resultant, on the first vector, if I express this in unit vectors, all 500 is in the x direction. So 500i, and just for emphasis, there would be nothing in the j or the y direction, so there's just a 0 there. 200, it has both an x and a y. We're going to use a cosine to find the x. So 200 cosine 30 degrees, and that's going to be the x component, so I'll just tag that with an I. And then 200 sine 30 degrees, and I will tag that with a j because that's the y component. Moving on to the third vector, the x component now is going to be on the opposite side of our triangle. If I draw out the triangle, x component here, which means we're going to use a sine to be able to get that. So then 300 sine 30 degrees, that's going to be the x component, so I'll tag that with an I. And then the y component, that's going to be a 300 cosine 30 degrees, so I'll tag that with a j. So we've streamlined all the x1, x2, y1, y2, all that stuff that we wrote out. We put it now in all one line using the I and j tags. Now we're going to get values. So then I have a 500i. I'm just going to leave the 0 out. And then on our next one, we've got, that'll be a 173.21i. And then the 200 sine, that's just going to be 100j. And then on to our third vector. And I'm going to back up here for 1 second because this is not a 30-degree angle. This is a 40-degree angle. So before we get too far in, we're going to fix that. So then 300 sine 40 degrees will give us a 192.84. And we'll tag that with an I. And then negative, because this is going downward, the 300 cosine 40 degrees is going to give us negative 147.08. That's in the y direction, so I'll tag that with a j. Now, everything is numbers, so now we can just go along and grab everything that is an I term and just combine them, and everything that is a j term and just combine them to be able to get our answer. So when we combine all of the i's, 866.04i. When we combine the j's, negative 47.08j. That is our answer as a unit vector because it describes both the magnitude in the x and the y, and with the i's and the j's, it describes the direction. If you want to take this from the unit vector form and put it back into a magnitude and direction, then you're going to take those two values and just draw it out as a triangle. So then here below, that would be 866.04 in the I direction, or the x direction. I'm going to slide that up because I have to go down. And then 47.08 in the y direction. So then our resultant here would be right across there. And the angle we would need to find using a tangent of theta would be that angle I just marked, theta. So when you do Pythagorean theorem and then tangent of theta, you could also express the answer as 867.32 kilometers at 3.11 degrees south of east. Both answers are correct. They are just written in different forms. Studying the migration patterns of humpback whales from your lab on the coast of Virginia, and you get these different positions: 4.2i minus 7j, and then 2 weeks later, 5.3i plus 2j. Giving us a little more space, we have our two vectors, R1 and R2, our time period delta t, 2 weeks. First thing we want to do is sketch and label the two position vectors. Just a side note, these are position vectors. So the whale is at one location and then at another location. Unlike the last problem where those were displacement vectors, the airplane had actually moved through those vectors. The whale hasn't moved through those vectors. It just happens to be at those two locations. For example, on R1, 4.2i minus 7j. That means I'm going to go over in the x direction about 4.2 and then down in the y direction about 7. So then that would lead me to a location right there. So then from the origin, R1, our whale is located there at that first time period. 2 weeks later, the whale has moved from that location to 5.3i. So if I go out to about 5.3 and then up to in the y direction, that will put me right in that neighborhood. 2 weeks later, then the whale has moved to this location. So then the actual displacement of the whale from position 1 to position 2, that's going to be the actual displacement. Whether the whale went in a straight line or not, it doesn't make any difference. That is the displacement of the whale. Now, in part B, we want to find that displacement. Well, we can't do what we did in the last one. In the last one, we basically took R1 and R2 and R3, and we added those vectors together. So here we're adding R1 to R2, and here we're adding R2 to R3. We combined those because the airplane had moved through those. If we think along the same lines, if we were to add here R1 plus R2, I'm just going to pick up R2 vector and I'm going to move it down there. Well, adding them together would get us out there. That's nowhere near where the whale is actually located. So we do not want to do an addition. If you think in terms of the base definition of, for example, like a delta x. Delta x, that would just be an x2 value minus an x1 value. Well, in this case, it's not a delta x, it's a delta r, which is going to be r2 minus r1. So if I pick up my vectors, r2, and I want to add to it a negative r1, well, then I'm going to pull my r1 vector down. I'm going to make it negative, so I'm going to flip it completely around. And that's going to get me a combination like this. Well, manipulating these over here, that gets us exactly what our vector is. So that's what we're going to end up doing here. In part B, delta r, r2 minus r1. So then if I take my 2 unit vectors, r2, 5.3i plus 2j, minus r1, 4.2i minus 7j, Now, we don't have any trig to do. This is a straightforward, just mathematical combination. The i's, 5.3 minus 4.2, that's going to give me 1.1 I. The j's, 2i minus a negative 7j, that's going to be 2 plus 7, that's going to be plus 9j, and that's going to be our resultant vector. So if you think about it, for my resultant vector up here on the diagram, I moved 1.1 to the right, and I moved 9 upward in the j direction to be able to get to the other end of that resultant. That's what that's telling you. Now, C, find the whale's average velocity. Average velocity, that would be displacement over time. In this case, our displacement is a delta r, and then over delta t. We just found delta r above, so we can just take that value as a unit vector and use that. 1.1 I plus 9j, and then our time period up here, 2 weeks. I think just for logical analysis, I'm going to convert that to days, and then we can express our answer in kilometers per day. If you left it in weeks or changed it to something else, it would still be equivalent. So 2 weeks, that would be 14 days. So then if we divide that, we're going to get 0.79 I plus 0.64 j. That's our answer, and then on a unit vector to express the units, you'll put just in parentheses afterwards, in this case, kilometers per day. So then basically, everything we did with vectors last year still applies. The only difference is we're using unit vectors, which significantly streamlines all of our ways of thinking and writing things out that we did last year. If you have questions on any of this, we will regroup and kind of go over this together on Friday, or you can send me an email and I'll address any questions that way. Ponder Physics.